When we think about exploring other worlds, Mars dominates the conversation. Rovers crawl across its rusty surface, billionaires promise colonies within decades, and NASA plans human missions for the 2030s. Mars gets the spotlight, the funding, and the dreams of becoming humanity's second home. But while we obsess over the red planet, we've turned our backs on a world that might hold far more important answers, a planet that could reveal why Earth became a paradise, while its twin became hell. Venus, our closest planetary neighbour, sits just 25 million miles away at its nearest approach, yet we treat it like a forgotten relative. We've sent more missions to Mars, which is on average 140 million miles distant, than to the scorching world next door. This isn't just an oversight, it's a potentially catastrophic blind spot in our understanding of how planets evolve, how atmospheres collapse, and ultimately, how Earth itself might change. Venus wasn't always the hellscape we see today. Evidence suggests it once had oceans, a temperate climate, and conditions that could have supported life. Then something went catastrophically wrong, transforming it into a 900-degree furnace with crushing atmospheric pressure and clouds of sulfuric acid. If we want to understand what could happen to Earth as our own climate shifts, Venus isn't just interesting, it's essential. The story of how Venus died might be the key to keeping Earth alive. The runaway greenhouse effect. Venus today is the hottest planet in the solar system despite being nearly twice as far from the Sun as Mercury. Its surface temperature reaches 900 degrees Fahrenheit, hot enough to melt lead and turn rock surfaces red with heat. This extreme temperature results from the most powerful greenhouse effect known in our solar system, a cautionary tale written in planetary physics. The mechanism is elegantly simple but devastatingly effective. Venus's thick atmosphere, composed of 96% carbon dioxide, traps infrared radiation emitted by the planet's surface. Unlike Earth, where greenhouse gases make up less than 1% of the atmosphere, Venus's entire atmospheric composition creates an insulating blanket so effective that heat cannot escape back into space. The incoming solar energy gets absorbed by the surface, re-radiated as infrared, and immediately trapped by the carbon dioxide molecules. This process repeats endlessly, with each cycle adding more heat to an already scorching system. The temperature remains constant whether on the day side facing the sun or the night side in darkness, whether at the equator or the poles. This uniform heat distribution reveals just how efficiently the thick atmosphere circulates and retains thermal energy. Computer models reconstructing Venus's atmospheric evolution show this wasn't always the case. Billions of years ago, Venus likely had temperatures comparable to early Earth, with liquid water pooling in lowland basins and a thinner, more balanced atmosphere. The transformation began when volcanic activity released massive amounts of carbon dioxide and water vapor into the atmosphere. On Earth, carbon dioxide gets absorbed by oceans and locked into carbonate rocks through chemical weathering, creating a natural regulatory cycle. Venus's proximity to the Sun meant slightly higher temperatures from the start, and this small difference triggered a catastrophic chain reaction. As temperatures rose, any existing oceans began to evaporate more rapidly. Water vapor itself is a greenhouse gas, and its increasing concentration in the atmosphere traps even more heat, which causes more evaporation, which releases more water vapor, a positive feedback loop with no natural break. Eventually, temperatures exceeded the point where liquid water could exist at any altitude or latitude. The planet's oceans evaporated completely, dumping millions of years' worth of stored water into the atmosphere. Without liquid water to help remove carbon dioxide from the atmosphere, volcanic emissions accumulated unchecked. The carbon dioxide concentration increased from trace amounts to total atmospheric dominance. Upper atmospheric water molecules, bombarded by solar ultraviolet radiation, broke apart into hydrogen and oxygen. The lightweight hydrogen escaped to space while the oxygen reacted with surface rocks or combined with other atmospheric constituents. What remained was a carbon dioxide hell. The atmosphere thickened to 92 times Earth's sea level pressure, the equivalent of being nearly a kilometre underwater in Earth's oceans. This immense atmospheric mass, combined with the greenhouse effect, pushed surface temperatures past any level where organic chemistry could function. The runaway greenhouse effect on Venus represents the ultimate climate tipping point, the boundary beyond which no recovery is possible. Planetary scientists use Venus as a natural laboratory for understanding feedback loops in climate systems. The mechanisms that destroyed Venus's habitability, greenhouse gas accumulation, water vapor feedback, loss of carbon sinks operate on Earth as well, just at vastly different scales and rates. By studying how Venus crossed the point of no return, researchers can identify warning signs and thresholds in Earth's own climate system. The lesson from Venus is clear. Atmospheres have tipping points, and once crossed, the changes become self-perpetuating and irreversible on timescales relevant to life. The crushing atmospheric pressure. Standing on Venus's surface would feel like being crushed under nearly a kilometre of ocean water. The atmospheric pressure reaches 92 bars, 92 times what we experience at sea level on Earth. This isn't just uncomfortable, it's mechanically destructive, powerful enough to crumple spacecraft like tin cans and compress any unprotected structure into a fraction of its normal volume. This crushing pressure results from the sheer mass of Venus's atmosphere. While Earth's atmospheric column extends upward for hundreds of kilometers before thinning to near vacuum, Venus's carbon dioxide atmosphere is both much denser and much deeper. The total mass of gas above each square meter of Venus's surface far exceeds the equivalent column on Earth. The carbon dioxide molecules, each heavier than the nitrogen and oxygen that dominate Earth's air, pack together under their own weight, creating pressure that increases dramatically toward the surface. Soviet Venera landers, the only spacecraft to successfully return images from Venus's surface, experienced this pressure firsthand. Engineers designed these probes with thick spherical pressure vessels, similar to deep ocean submersibles. The Venera 13 and 14 landers, which touched down in 1982, survived for just over 2 hours before the combination of heat and pressure overwhelmed their systems. Their cameras captured images of a flat, rock-strewn landscape bathed in orange light filtered through the thick atmosphere above. The rocks themselves showed signs of chemical weathering from the corrosive atmospheric gases, their surfaces etched and altered by reactions that occur only at Venus's extreme conditions. The pressure affects everything about the environment. Gas density approaches that of supercritical fluids, where the distinction between gas and liquid begins to blur. At the surface, Venus's carbon dioxide exists in a state similar to the supercritical carbon dioxide used in industrial extraction processes, dense enough to have significant solvent properties but still able to flow like a gas. This strange intermediate state affects how heat transfers through the lower atmosphere and how materials interact with their surroundings. Wind patterns near the surface move slowly despite the dynamic circulation higher up, because the air is so dense that even slow movement carries enormous momentum. Surface wind speeds typically measure only a few kilometers per hour, yet these sluggish flows carry enough mass and energy to gradually erode rock formations over geological time. The pressure gradient through Venus's atmosphere reveals the planet's unique structure. At 50 kilometers altitude, pressure drops to approximately 1 bar equal to Earth's sea level. This region, often called the habitable zone of Venus's atmosphere, maintains temperatures around 60 degrees Fahrenheit, despite being suspended above a hellish surface. The pressure continues to decrease with altitude, following predictable physics, but the density remains higher than Earth's atmosphere at equivalent pressures due to carbon dioxide's molecular weight. Atmospheric scientists studying Venus use pressure measurements to map atmospheric structure and circulation patterns. The pressure distribution affects cloud formation, chemical reactions, and how energy transfers between different layers. The Soviet Venera missions carried barometers that recorded pressure continuously during their descents, creating vertical profiles that revealed unexpected structure in what appeared from space to be a uniform, featureless atmosphere. Understanding Venus's pressure regime matters for future exploration. Any surface mission must contend not just with heat, but with mechanical forces capable of destroying conventional spacecraft components. Engineers designing Venus landers study the Venera designs, looking for ways to extend survival time through better insulation, stronger pressure vessels, and cooling systems that can function briefly in such extreme conditions. The pressure also affects scientific instrumentation, spectrometers, cameras, and chemical sensors all must function while being compressed with thousands of pounds of force per square inch. Recent concepts for Venus missions include high-altitude balloons that would float in the more moderate conditions at 50 kilometers altitude, avoiding the surface pressure entirely while still conducting valuable atmospheric science. These balloons would drift in Venus's fast-moving clouds, carried around the planet by winds that circumnavigate the globe in just 4 Earth days despite Venus's own slow rotation, the mysterious superrotation. Venus rotates on its axis once every 243 Earth days, slower than its orbital period around the Sunday. A day on Venus literally lasts longer than a year, and the planet rotates backward compared to most planets, making the sun rise in the west and set in the east. This sluggish rotation should create weak atmospheric circulation with minimal global wind patterns, yet Venus's atmosphere exhibits the solar system's most extreme superrotation. The upper atmosphere races around the planet once every 4 Earth days, travelling at speeds exceeding 200 miles per hour, while the solid surface below barely moves. This is superrotation, atmospheric winds moving dramatically faster than the planet's rotation, and despite decades of study, scientists still debate the precise mechanisms that drive it. The phenomenon becomes visible in ultraviolet images of Venus's cloud tops. Dark, Y-shaped patterns formed by unknown ultraviolet absorbers trace the atmospheric circulation, rotating around the planet and completing full circuits in about 4 days. These patterns reveal a coherent planet-wide wind system that maintains its speed, despite Venus's minimal rotation, violating simple expectations from atmospheric dynamics. On Earth, the Coriolis effect generated by our planet's rotation organizes winds into recognizable patterns. Trade winds, jet streams, and rotating storm systems all derive their structure from Earth's 2-4-hour rotation. Venus's 2-4-3-day rotation produces almost negligible Coriolis forces, yet its atmosphere organizes into stable, high-speed circulation. The leading explanation invokes thermal tides, atmospheric waves driven by solar heating rather than gravitational effects. As the sun slowly moves across Venus's sky during its long day, it heats the atmosphere unevenly, creating pressure differences that drive winds. But instead of simply moving from hot to cold regions, the thick atmosphere responds by developing wave patterns that extract momentum from the solar heating and transfer it to the atmospheric circulation. These waves, moving through the dense carbon dioxide, gradually accelerate the upper atmosphere until it reaches equilibrium at superrotational speeds. Computer simulations of Venus's atmosphere can reproduce superrotation when they include detailed physics of radiative heating, atmospheric waves, and momentum transfer. These models show that once superrotation begins, it becomes self-sustaining. The fast-moving upper atmosphere transports heat efficiently from the day side to the night side, maintaining the planet's uniform temperature distribution. The circulation patterns also generate waves that propagate downward, coupling the upper and lower atmosphere despite their different speeds. Observations from multiple missions have mapped Venus's superrotation at different altitudes and latitudes. The Venus Express spacecraft, which orbited from 2006 to 2014, tracked cloud features and measured wind speeds across the planet. It found that superrotation extends deep into the atmosphere, with wind speeds decreasing gradually with depth, but remaining significant even in the middle atmosphere. The fastest winds occur at the equatorial cloud tops, where speeds can exceed 250 miles per hour. At higher latitudes, speeds decrease, creating a pattern where the equatorial regions circle the planet fastest while polar regions lag behind. This differential rotation generates enormous wind shear between latitudinal bands, creating turbulence and mixing that affects cloud formation and chemical distribution. Recent observations from Japan's Akatsuki spacecraft, orbiting Venus since 2015, have revealed previously unknown details about atmospheric waves and circulation patterns. Akatsuki's infrared and ultraviolet cameras detected gravity waves propagating through the atmosphere, generated by flow over Venus's highland regions. These waves carry energy and momentum upward, potentially contributing to the maintenance of superrotation by transferring angular momentum from the surface to the upper atmosphere. The spacecraft also observed a massive stationary wave pattern in the atmosphere above Venus's largest highland region, Aphrodite Terra. This bow-shaped feature, extending thousands of kilometers, results from atmospheric flow disrupted by the underlying topography. Despite the surface moving at just a few miles per hour relative to the Sun, it's moving through the atmosphere fast enough to generate waves similar to those formed when wind flows over mountains on Earth. Understanding superrotation matters beyond pure planetary science. It represents an extreme example of atmospheric dynamics that challenges our theories of how atmospheres behave. Climate models for Earth and exoplanets must account for the possibility that under certain conditions, atmospheres can develop circulation patterns dramatically different from those driven primarily by planetary rotation. Some exoplanets discovered around other stars likely experience conditions similar to Venus: thick atmospheres, slow rotation, intense heating. Superrotation might be common on such worlds, affecting their climate, habitability, and observable characteristics. The sulfuric acid clouds. Venus's clouds are not made of water. They consist primarily of concentrated sulfuric acid droplets, forming continuous decks that completely obscure the surface and create the planet's brilliant appearance in visible light. These clouds exist between 45 and 70 kilometers altitude, organized into distinct layers with different droplet sizes and compositions. The upper clouds, thickest and most opaque, extend from about 65 to 70 kilometers. Middle clouds occupy the 50 to 65 kilometer range, while lower haze layers reach down to 45 kilometers. Below this altitude, the temperature becomes too high for sulfuric acid droplets to remain stable, and they evaporate back into gaseous components. The formation of these clouds begins with sulfur dioxide gas released by volcanic activity on Venus's surface. This gas rises into the atmosphere where ultraviolet radiation from the sun drives chemical reactions that convert sulfur dioxide into sulfur trioxide. The sulfur trioxide then combines with water vapor to form sulfuric acid vapor, which condenses into tiny droplets as temperatures decrease with altitude. The process mirrors acid rain formation on Earth but on a planetary scale, creating permanent cloud decks rather than occasional precipitation. The concentration of sulfuric acid in the cloud droplets reaches 75 to 90%, approaching the concentration of battery acid. These droplets never reach the surface as rain because the intense heat in the lower atmosphere evaporates them completely. Instead, sulfuric acid exists in a continuous cycle. Droplets form in the cooler upper atmosphere, grow as vapor condenses onto them, fall toward the surface while gradually evaporating, and release their sulfur and water back into gaseous form to rise and repeat the cycle. The clouds contain more than just sulfuric acid. Spectroscopic observations have detected elemental sulfur, sulfur dioxide, and mysterious compounds that absorb ultraviolet light strongly but remain chemically unidentified. These unknown ultraviolet absorbers create the dark, Y-shaped patterns visible in UV images, moving with the superrotating winds and changing shape over periods of days. Decades of speculation have proposed various candidates for these absorbers: sulfur allotropes, polysulfur compounds, iron chloride, even biological pigments in some fringe hypotheses, but definitive identification remains elusive. Sample return missions or sophisticated in situ chemical analysis would be needed to conclusively identify these compounds. The clouds affect Venus's energy balance profoundly. They reflect about 75% of incoming sunlight back to space, making Venus the most reflective planet in the solar system. This high reflectivity, or albedo, limits the amount of solar energy entering the system despite Venus's proximity to the Sunday. Without these reflective clouds, Venus would absorb much more sunlight and become even hotter than it already is. The clouds also trap infrared radiation from the surface, contributing to the greenhouse effect, though the massive carbon dioxide atmosphere provides most of the heat retention. The structure of the cloud decks varies with latitude and over time. Near the poles, the clouds thin somewhat, creating relatively clearer regions where infrared radiation can escape more efficiently. This contributes to the development of enormous vortex structures at both poles, swirling atmospheric features resembling hurricanes but powered by different mechanisms. These polar vortices, discovered by the Pioneer Venus and Venus Express missions, show complex dynamics with multiple nested circulation cells and temperature structures that remain poorly understood. Observations through the clouds using radar and infrared instruments reveal that Venus's surface contributes to atmospheric chemistry. Radar mapping from the Magellan spacecraft and Earth-based telescopes shows that highland regions have different radar reflectivity than lowlands, suggesting compositional differences possibly related to chemical reactions with the atmosphere. Certain minerals remain stable at the surface under Venus's extreme conditions, while others react with atmospheric gases, creating patterns that vary with altitude and temperature. Some researchers have proposed that the weathering of specific rock types might release chemicals into the atmosphere that eventually contribute to cloud formation or affect the atmospheric chemistry at different altitudes. the volcanic resurfacing event. Venus's surface is remarkably young, perhaps only 300 to 600 million years old, despite the planet being 4.5 billion years old like the rest of the solar system. This presents a geological puzzle because impact craters from asteroids and comets should accumulate steadily over time, creating increasingly cratered terrain similar to the Moon or Mercury. Instead, Venus shows approximately 1,000 impact craters distributed randomly across its surface, far fewer than expected for an ancient surface. The explanation involves catastrophic volcanic resurfacing that buried the older, heavily cratered surface beneath vast plains of fresh lava. Radar mapping from NASA's Magellan spacecraft, which orbited Venus from 1990 to 1994, revealed this young surface in stunning detail. The images showed enormous volcanic plains covering about 85% of the planet, vast lava flows extending for thousands of kilometers, and volcanic features unlike anything found on Earth. Massive shield volcanoes, some rivaling or exceeding the size of Hawaii's Mauna Loa, dot the landscape. Pancake domes flat, circular volcanic constructs formed from viscous lava cluster in certain regions, their smooth tops and fractured edges indicating formation from lava too thick to flow like basalt. The crater distribution provides timing constraints. If Venus had been volcanically active continuously like Earth, with localized eruptions creating new terrain while leaving other regions unchanged, we would observe a mix of heavily cratered old surfaces and crater-free young surfaces. Instead, the craters were distributed randomly with no clustering or obvious age patterns, suggesting the entire planet underwent resurfacing within a relatively short geological period, perhaps 100 million years or less. After this global resurfacing event, volcanic activity apparently decreased to much lower levels, allowing craters to accumulate without being buried by new lava flows. Why Venus experiences episodic global resurfacing while Earth has continuous plate tectonics remains debated. The key difference likely involves how each planet releases its internal heat. Earth's lithosphere, the rigid outer shell, breaks into plates that move relative to each other, subducting old crust into the mantle and creating new crust at mid-ocean ridges. This process continuously recycles the surface and releases heat through distributed volcanic activity. Venus lacks evidence of plate tectonics. Its lithosphere appears to be a single, unbroken shell covering the entire planet. Heat from the interior can't escape efficiently through this stagnant lid, so it builds up until the lithosphere becomes hot and weak enough to allow massive volcanic eruptions that resurface large portions of the planet simultaneously. Computer models of Venus's thermal evolution support this scenario. Starting with a stagnant lid, heat accumulates beneath the lithosphere over hundreds of millions of years. Eventually, the temperature increases enough that the base of the lithosphere begins to melt or become mechanically weak. Volcanic activity intensifies, breaking through the surface in numerous locations and flooding vast regions with lava. This releases the accumulated heat, the lithosphere cools and solidifies into a new stagnant lid, and the cycle begins again. The models suggest resurfacing events might occur every 500 million to 1 billion years, consistent with the observed surface age. The volcanic features observed on Venus provide evidence for this activity. Large volcanic structures called coronae circula features hundreds of kilometers across with concentric ridges and central volcanic domes number in the hundreds. These likely form when hot mantle plumes rise toward the surface, uplifting the crust and triggering volcanism before the region subsides. Rift zones, where the crust has been pulled apart by extensional forces, expose deep crustal layers and show evidence of past lava flows. Some regions show features interpreted as possible cryovolcanism, volcanic activity involving volatile substances rather than pure molten rock, though confirming this requires more detailed study. The evidence for recent or ongoing volcanism comes from indirect observations. Measurements from Venus Express detected variations in sulfur dioxide concentration in the upper atmosphere, with amounts fluctuating over several years. Sulfur dioxide is released by volcanic eruptions, and it gets destroyed by photochemical reactions in the atmosphere within years to decades. The observed variations suggest either sporadic volcanic activity injecting fresh sulfur dioxide, or variations in atmospheric circulation patterns bringing deeper, sulfur-rich air to the upper atmosphere where measurements occur. Definitive detection of active volcanism, requires direct observation of lava flows or volcanic plumes, which no mission has yet achieved. Future missions equipped with infrared cameras might detect the thermal signature of fresh lava or catch volcanic eruptions in progress. The backward rotation mystery. Venus spins backward. While Earth, Mars, Jupiter, and most solar system bodies rotate counterclockwise when viewed from above their north poles, Venus rotates clockwise, a retrograde rotation unique among the planets. Combined with its extremely slow rotation period of 243 Earth days, this makes Venus one of the solar system's most peculiar rotators. The standard model of planet formation can't easily explain retrograde rotation. Planets form from rotating disks of gas and dust around young stars, and this rotation imparts angular momentum to the forming planets, causing them to spin in the same direction as their orbital motion. Venus should have started with prograde rotation like its siblings, so something must have reversed or radically altered its spin. Several mechanisms could produce retrograde rotation. The leading hypothesis invokes giant impacts collisions with large planetary bodies during the final chaotic stages of terrestrial planet formation. Computer simulations show that a sufficiently massive impact at the right angle and velocity could transfer enough angular momentum to reverse a planet's rotation. Earth experienced such a collision, the giant impact that created the Moon, which tilted our rotation axis but didn't reverse it. Venus might have suffered one or more impacts that did reverse its spin, perhaps in combination with tidal forces from the Sun that subsequently slowed the rotation to its current leisurely pace. The slow rotation itself presents another puzzle. Tidal interactions between a planet and the Sun, or nearby satellites, gradually transfer angular momentum, typically locking the rotation period to the orbital period, as the Moon is locked to Earth. Venus has no large satellite to create strong tidal forces, but the Sun's tidal pull on Venus's thick atmosphere might have played a role. Atmospheric tides, bulges in the atmosphere created by solar heating, experience drag from the planet's surface. This transfers angular momentum between the atmosphere and the solid planet, gradually slowing the rotation. Models incorporating these effects can produce the observed slow rotation over billions of years, but they typically require the planet to start with already slow rotation from giant impacts or other processes. Another factor complicating Venus's rotation is the interaction between its thick atmosphere and the solid planet. Venus's atmosphere contains enormous angular momentum due to superrotation, with the upper atmosphere circling the planet every 4 days, while the surface barely rotates. This creates complex momentum exchange between atmospheric layers and the surface. Some researchers propose that atmospheric dynamics could have influenced the planet's rotation rate over geological time, though the mechanisms remain poorly understood. The dense atmosphere might also affect how tidal forces operate, changing the timescales and outcomes compared to planets with thinner atmospheres. Measurements from spacecraft orbiting Venus have refined our knowledge of its rotation. The rotation period varies slightly over time, tens of seconds, due to exchange of angular momentum between the atmosphere and the solid planet. When the atmospheric superrotation speeds up or slows down, conservation of angular momentum requires the solid planet to respond by changing its rotation rate in the opposite direction. These variations, detected by tracking surface features in radar images from different orbital missions separated by decades, reveal that Venus's atmosphere and interior remain dynamically coupled despite the vast difference in their rotation rates. The retrograde rotation affects Venus's magnetic field, or rather, the absence of one. Earth's magnetic field generates through a dynamo process in the liquid iron outer core, driven by convection and sustained by the planet's rotation. Venus likely has a similar liquid iron core, and early in its history might have generated a magnetic field through a similar dynamo. However, the extremely slow rotation provides insufficient Coriolis force to organize convective flows into the patterns needed to sustain a dynamo. Measurements from multiple spacecraft confirm that Venus lacks a significant intrinsic magnetic field, only a weak induced field created by the interaction of the solar wind with the upper atmosphere. The missing magnetic field. Venus possesses no global magnetic field, a surprising absence for a planet so similar to Earth in size and composition. Earth's magnetic field extends thousands of kilometers into space, deflecting the solar wind, a stream of charged particles from the Sun, and creating a protective magnetosphere. Venus has none of this protection. The solar wind impacts the upper atmosphere directly, creating a bow shock where the supersonic solar wind slows and flows around the planet, but without a magnetic barrier to prevent atmospheric erosion. This lack of magnetic shielding has profound consequences for Venus's atmospheric evolution and provides important insights into how planetary magnetic fields generate and why they sometimes fail. Earth's magnetic field originates in its liquid iron outer core through a self-sustaining dynamo process. Heat, escaping from the solid inner core, drives convective motion in the liquid iron. Earth's rotation organizes this convection through the Coriolis effect, creating helical flow patterns. These flowing electrical conductors generate electric currents, which produce magnetic fields, which interact with the flows to sustain and organize the convection, a self-reinforcing cycle that maintains the field over geological timescales. Venus should have a similar internal structure, an iron core that differentiated early in the planet's history, likely liquid in its outer portions due to the heat remaining from formation and radioactive decay, yet it produces no significant magnetic field. The key difference appears to be rotation rate. Venus's 2-4-3 day rotation provides almost negligible Coriolis force, insufficient to organize convective flows in the core into the coherent patterns needed for dynamo action. Computer simulations of planetary dynamos show that below a certain rotation rate threshold, convection becomes disordered and no longer generates a sustained magnetic field. Venus sits below this threshold. Early in its history, if Venus rotated faster before tidal forces and giant impacts slowed it down, it might have possessed a magnetic field. As rotation slowed, the dynamo would have failed and the field decayed away. Another possibility involves the state of the core itself. If Venus's core has completely solidified or remains entirely liquid without an inner solid core growing within it, the convective patterns needed for a dynamo might not develop. On Earth, the slow solidification of the inner core releases latent heat and light elements, driving vigorous convection in the outer core. If Venus's core evolution followed a different path, perhaps cooling more slowly due to different thermal conditions in the mantle, it might lack the driving forces necessary for a dynamo, regardless of rotation rate. The absence of a magnetic field exposes Venus's atmosphere to direct interaction with the solar wind. Measurements from multiple spacecraft have mapped how the solar wind shapes Venus's magnetosphere as actually an induced magnetosphere created by electric currents in the ionosphere, rather than a true magnetic field. The solar wind carries frozen-in magnetic field lines that drape around the planet, creating a comet-like magnetotail stretching millions of kilometers downwind. Within this structure, charged particles from the solar wind can enter the upper atmosphere and collide with atmospheric molecules, transferring energy and potentially stripping away atmospheric gas through a process called sputtering. Atmospheric escape through solar wind interaction provides a mechanism for Venus to lose volatiles over geological time. Lighter elements like hydrogen escape more easily, but even heavier atoms can be sputtered away if given enough energy by impacting solar wind particles. The Venus Express mission carried instruments specifically designed to study atmospheric escape, measuring the composition and velocity of particles flowing away from the planet. These measurements revealed complex escape processes, with hydrogen, oxygen, and even heavier ions like oxygen 1,6 and oxygen 1,8 detected in the escaping flux. The escape rates measured by Venus Express, while significant, represent only a tiny fraction of Venus's massive atmosphere lost per year. Extrapolating these rates backward over billions of years accounts for substantial atmospheric loss but cannot alone explain the complete loss of Venus's water. The enhanced deuterium to hydrogen ratio discussed earlier indicates most water loss occurred through photochemical breakup in the upper atmosphere and hydrogen escape, with solar wind interactions playing a secondary role. The magnetic field question matters for understanding exoplanets as well. Many rocky planets discovered around other stars likely have rotation rates, core structures, and thermal evolution different from Earth's. Some might lack magnetic fields despite being otherwise Earth-like. The presence or absence of a magnetic field could significantly affect a planet's ability to retain its atmosphere against stellar wind erosion, particularly for planets orbiting close to their stars where stellar radiation and particle flux can be intense. The phosphine detection controversy. In September 2020, astronomers announced the detection of phosphine gas in Venus's atmosphere, sparking immediate excitement and controversy. Phosphine, a molecule consisting of one phosphorus atom and 3 hydrogen atoms, is a biosignature gas on Earth, produced primarily by biological processes in anaerobic environments with few known abiotic production mechanisms. Its apparent detection in Venus's clouds raised the tantalizing possibility that microbial life might exist floating in the temperate cloud layers, protected from the hellish surface below. The claim relied on spectroscopic observations from the James Clerk Maxwell Telescope in Hawaii, protected from the hellish surface below. The claim relied on spectroscopic observations from the James Clerk Maxwell Telescope in Hawaii and the Atacama Large Millimeter, Submillimeter Array in Chile. The research team analysed millimeter wavelength light passing through Venus's atmosphere, looking for the characteristic absorption signature of phosphine at a wavelength of approximately 1 millimeter. They reported detecting a signal consistent with phosphine at an abundance of about 20 parts per billion in the cloud layers, around 50 to 60 kilometers altitude. The announcement immediately drew skepticism and intense scrutiny. Multiple research teams reanalyzed the original data and conducted their own observations, reaching conflicting conclusions. Some found the phosphine signal weaker than initially reported or consistent with other molecules like sulfur dioxide, which has absorption features at similar wavelengths. Others questioned the data processing methods, suggesting that noise in the measurements or calibration uncertainties could produce spurious signals. The original research team defended their analysis while acknowledging uncertainties in the abundance estimate. The scientific debate focused on two key questions. Is phosphine actually present, and if so, what produces it? Regarding the first question, subsequent observations using different telescopes and techniques produced mixed results. Some observations found no convincing phosphine signal, while others reported weak detections at lower abundances than initially claimed. The difficulty arises because phosphine's spectral signature at millimeter wavelengths overlaps partially with sulfur dioxide, which is abundant in Venus's atmosphere. Disentangling the two requires careful modelling of atmospheric conditions, line shapes, and radiative transfer, all subject to uncertainties when observing through Venus's thick, turbulent atmosphere. If phosphine exists in Venus's clouds, explaining its production presents challenges. On Earth, phosphine is produced by anaerobic bacteria in swamps, marshes, and animal digestive systems. It's also synthesized industrially but rarely found in nature outside biological contexts. Phosphorus, while present on Venus's surface in minerals, doesn't readily form phosphine through known abiotic chemistry at the temperatures and pressures in Venus's clouds. Lightning could potentially create small amounts through electrical discharge, and photochemistry driven by ultraviolet radiation might produce trace quantities, but calculations suggest these processes fall far short of explaining the reported phosphine abundance. The biological interpretation faces equally daunting challenges. Venus's clouds contain concentrated sulfuric acid droplets, an extremely hostile environment for any Earth-like life. While some terrestrial microorganisms tolerate acidic conditions, none survive in concentrated sulfuric acid. Additionally, the clouds lack liquid water, contain very little organic carbon, and experience intense ultraviolet radiation from the sunday. Any hypothetical Venusian microbes would require biochemistry fundamentally different from terrestrial life, perhaps using sulfuric acid as a solvent instead of water, and deriving energy from atmospheric chemistry rather than photosynthesis or conventional metabolism. Despite these obstacles, the possibility of aerial life on Venus isn't absurd. The cloud layers at 50 to 60 kilometers altitude maintain temperatures between 30 and 90 degrees Fahrenheit and pressures close to Earth's sea level, the most Earth-like environment in the solar system outside our own planet. Microorganisms could potentially exist as spores or droplets suspended in the clouds, remaining aloft indefinitely, while extracting nutrients from atmospheric gases and sulfuric acid droplets. Carl Sagan and Harold Morowitz proposed this scenario in 1967, long before the phosphine controversy, suggesting that Venus's clouds might harbour a tenuous biosphere, even as the surface remained sterile. The phosphine debate highlights the challenges of biosignature detection in planetary atmospheres. A single molecular detection, even if confirmed, cannot definitively prove biological activity without ruling out all plausible abiotic production mechanisms, a difficult standard when our knowledge of planetary atmospheric chemistry remains incomplete. The controversy has spurred proposals for new Venus missions equipped with instruments to sample the clouds directly, analyze their chemistry in detail, and search for phosphine and other potential biosignature gases, with greater sensitivity and specificity than remote observations allow. The cloud layer habitability zone. While Venus's surface represents one of the solar system's most hostile environments, its cloud layers present dramatically different conditions, so different that some astrobiologists consider them potentially habitable. At altitudes between 48 and 60 kilometers, Venus's atmosphere maintains temperatures ranging from 0 to 90 degrees Fahrenheit, pressures close to Earth sea level, and enough sunlight for photosynthesis. These are the most Earth-like conditions found anywhere beyond our planet, leading to serious scientific proposals that microbial life might exist floating in Venus's clouds. The concept of aerial biospheres isn't new. Scientists have speculated about the possibility since the 1960s, when early Venus missions revealed the contrast between the scorching surface and the temperate clouds. Carl Sagan and Harold Morovitz formally proposed the idea in 1967, suggesting that Venusian microorganisms might exist as spores or droplets permanently suspended in the atmosphere, reproducing and evolving without ever touching the surface. They envisioned a life cycle where microbes grow in the cloud layers, occasionally fall toward the hotter lower atmosphere where they sporulate, then get lofted back up by atmospheric circulation to germinate and resume metabolism. The environmental conditions at cloud level support this possibility. Temperatures in the 50-kilometer altitude range remain moderate, around 160 degrees Fahrenheit in the lower clouds, cooling to near freezing at the cloud tops. These temperatures allow organic chemistry to function and don't denature proteins or nucleic acids as surface temperatures would. The pressure matches Earth's surface pressure closely, eliminating the extreme compression that crushes spacecraft at the surface. Sunlight penetrates the upper cloud layers, providing energy that organisms might harness through photosynthesis or photochemistry. However, significant challenges confront any potential cloud-dwelling life. The clouds consist of concentrated sulfuric acid droplets, 75 to 90% sulfuric acid by mass. No known terrestrial organism can survive in concentrated sulfuric acid, which denatures proteins, degrades nucleic acids, and disrupts cellular membranes. Some bacteria tolerate acidic conditions down to pH values near zero, but even these extremophiles require liquid water and cannot function in nearly pure acid. Hypothetical Venusian life would need biochemistry adapted to acidic environments far beyond anything found on Earth, perhaps using different solvents, protective coatings, or chemical strategies to isolate reactive cellular machinery from the surrounding acid. Water availability poses another problem. The clouds contain water vapor, but in limited amounts, typically less than a few hundred parts per million. Terrestrial life requires abundant liquid water for metabolic processes, cell structure, and reproduction. Venusian organisms would need to extract scarce water vapor from the atmosphere, or perhaps use sulfuric acid itself as a solvent, requiring fundamental biochemical differences from all known life. Carbon sources present similar challenges. Venus's atmosphere contains carbon dioxide in abundance, which organisms could theoretically fix into organic molecules as plants do on Earth. However, the lack of liquid water complicates this process since terrestrial photosynthesis operates in aqueous solutions. Alternative biochemistries using sulfuric acid as a solvent might enable carbon fixation, but no examples exist to demonstrate feasibility. Despite these obstacles, the clouds contain complex chemistry. The unknown ultraviolet absorbers that create Venus's Y-shaped cloud patterns remain unidentified after decades of study. Spectroscopic observations have ruled out many simple molecules, leaving possibilities that include sulfur compounds, polycyclic aromatics, or even organic pigments. Some researchers have proposed that these UV absorbers might be biological in origin pigments produced by microorganisms to protect themselves from solar radiation, analogous to how some terrestrial bacteria produce pigments for UV protection. This remains highly speculative without direct sampling and chemical analysis. Proposed mechanisms for maintaining aerial life include reproduction within cloud droplets, with organisms using the sulfuric acid environment for metabolism, and occasionally being transported to different altitudes by convection. As droplets fall toward the hotter, lower atmosphere, organisms might sporulate or become dormant, then reactivate when turbulence or convection carries them back to habitable altitudes. This life cycle would need to balance the competing processes of gravitational settling and atmospheric mixing, maintaining a population despite continuous losses to the uninhabitable regions above and below the clouds. The case for cloud-based life remains speculative but not impossible. Earth's own atmosphere harbours microorganisms at high altitudes, carried aloft by winds and surviving for extended periods in cloud droplets before settling back to the surface. Venus's clouds, despite their acidic composition, provide more stable conditions than Earth's atmosphere: no freezing temperatures, more consistent pressure, and permanent cloud cover rather than ephemeral clouds. If life arose on Venus during its potentially habitable past when oceans existed, some organisms might have adapted to increasingly harsh conditions as the planet transformed, ultimately retreating to the only remaining habitable niche, the clouds. The bizarre surface composition. Venus's surface composition reveals a world of basaltic lava plains, highland plateaus, and volcanic features, but the chemistry differs from simple expectations in subtle ways that suggest ongoing interaction between surface rocks and the hostile atmosphere. Soviet Venera landers provided the only direct measurements of surface composition when they analysed rock samples at several landing sites in the 1970s and 1980s. These measurements revealed rocks similar to terrestrial basalts, igneous rocks rich in iron, magnesium, and calcium, consistent with volcanic resurfacing. However, unusual variations in composition between landing sites and peculiar weathering patterns visible in images suggest more complex surface chemistry. The Venera 13 and 14 landers used X-ray fluorescent spectrometers to determine elemental abundances in rocks at their landing sites in the lowland plains. The results showed typical basaltic compositions with silicon dioxide around 45% by mass, similar to ocean floor basalts on Earth. Aluminum, iron, magnesium, and calcium occurred in proportions consistent with mantle-derived volcanic rocks. However, the measurements revealed higher potassium and sulfur contents than typical terrestrial basalts, suggesting either unusual mantle chemistry or alteration by atmospheric interaction. Venera 8 landed in a highland region and analysed rocks with higher silicon dioxide content, around 60% more similar to granitic continental rocks on Earth. This compositional difference between highlands and lowlands mirrors Earth's dichotomy between basaltic ocean floors and silica-rich continents, but the mechanisms producing such variation on Venus remain uncertain. Earth's continents form through plate tectonics, with subduction and partial melting producing evolved magmas rich in silica. Venus lacks plate tectonics, so the highland material might form through different processes, perhaps partial melting of the crust, impact melt sheets from large collisions, or ancient volcanic processes that operated differently in Venus's past. The surface weathering visible in Venera images shows rocks with flaky, layered textures, unlike fresh volcanic rocks. Some researchers interpret these features as chemical weathering products formed by reactions between minerals and atmospheric gases. At Venus's surface, carbon dioxide and sulfur dioxide can react with certain minerals, altering their structure and producing secondary minerals not stable under Earth conditions. For example, calcite calcium carbonate forms readily from reactions between calcium-rich rocks and carbon dioxide at high temperatures and pressures. Pyrite and other sulfide minerals can form from sulfur dioxide reacting with iron-rich rocks. Radar observations from Magellan revealed that Venus's highlands show unusually high radar reflectivity at certain wavelengths, suggesting the presence of minerals with specific dielectric properties. One interpretation invokes ferroelectric minerals materials whose electrical properties change with temperature that become particularly radar reflective under Venus's surface conditions. Candidates include minerals containing iron oxides or sulfides formed through atmospheric weathering. The reflectivity variations correlate with altitude, with the most reflective materials concentrated at high elevations where temperatures drop below certain thresholds. This temperature-dependent reflectivity suggests minerals undergoing phase transitions or chemical reactions near specific temperature boundaries. Another peculiarity involves the apparent absence of certain minerals that should be stable at Venus's surface. Olivine and pyroxene, common silicate minerals in basaltic rocks, should occur abundantly based on the measured compositions, yet their spectroscopic signatures aren't strongly detected in near-infrared observations of the surface. This absence might indicate that surface rocks have weathered to form secondary minerals, or that coatings of other materials obscure the underlying mineralogy. Proposed coating materials include hematite iron oxide, which forms from weathering of iron-bearing silicates in the presence of oxygen or sulfur compounds. Recent reanalysis of Venera data and radar observations suggests that some highland regions might contain tesserae complexly deformed terrain blocks, showing evidence of extensive tectonic deformation. The composition of tesserae remains unknown, but some researchers speculate they might represent ancient crust preserved from Venus's earlier geological history, possibly including rocks formed when the planet had liquid water and different atmospheric chemistry. Testing this hypothesis requires sample return missions or advanced landers capable of detailed mineralogical analysis. The interaction between Venus's surface and atmosphere operates on geological timescales, with atmospheric gases slowly reacting with exposed minerals and volcanic eruptions periodically injecting fresh material into the atmosphere. The equilibrium between these processes determines atmospheric composition and surface mineralogy simultaneously. Changes in volcanic activity alter the amounts of sulfur dioxide and water vapor in the atmosphere, which in turn affects weathering rates and the types of minerals stable at the surface. Understanding these coupled systems requires integrated studies of atmospheric chemistry, volcanic processes, and surface composition, a challenge given the difficulty of conducting long-duration measurements in Venus's extreme environment. The Magellan radar discoveries. NASA's Magellan spacecraft transformed our understanding of Venus's surface through the most comprehensive radar mapping campaign ever conducted at another planet. Orbiting Venus from 1990 to 1994, Magellan used synthetic aperture radar to image 98% of the surface at resolutions down to 100 meters, revealing geological features, volcanic structures, and tectonic patterns in unprecedented detail. The mission's discoveries fundamentally changed how planetary scientists view Venus's geological evolution and continue to guide research decades later. Radar imaging proved essential for studying Venus because conventional cameras cannot penetrate the thick cloud cover. Radar sends electromagnetic pulses toward the surface and records the reflected signals, with the strength and timing of reflections encoding information about surface texture, composition, and topography. Smooth surfaces reflect radar poorly while rough surfaces scatter radar efficiently, creating contrast in the images. Different minerals and rock types affect radar reflections through their electrical properties, adding compositional information. Magellan's images revealed Venus as a world dominated by volcanic features. Vast lava plains cover most of the planet, created by fluid basaltic lava flows similar to those forming ocean floors on Earth. These plains show varying textures, some smooth with few superimposed features, others crossed by ridges, fractures, and channels. Thousands of volcanic edifices dot the landscape, ranging from shield volcanoes hundreds of kilometers across to smaller volcanic domes and cones. The largest shield volcanoes, like Mart Mons and Sapas Mons, rise 5 kilometers above the surrounding plains, their flanks covered with overlapping lava flows traceable for thousands of kilometers. Particularly striking are the pancake domes, circular volcanic features 10 to 20 kilometers across with flat tops and steep sides. These formed from extremely viscous lava extruded onto the surface, piling up rather than flowing away. The composition of the lava must differ from the basaltic flows forming the plains, possibly containing more silica which increases viscosity. Some pancake domes show radial fracture patterns on their tops, created as the hot lava cooled and contracted. Colonies circular to oval features hundreds of kilometers across, number in the hundreds. These complex structures show concentric ridges and fractures surrounding central volcanic domes and plains. They likely form when hot mantle plumes rise toward the surface, uplifting the crust and triggering volcanism before the region subsides and cools. The size and distribution of coronae provide clues about heat flow from Venus's interior and the vigor of mantle convection. Magellan also mapped extensive rift zones, elongated valleys bounded by parallel faults where the crust has been pulled apart. The largest, Paga Chasma, extends thousands of kilometers across the equatorial region, reaching depths of several kilometers. These rifts might represent the closest Venus comes to plate boundaries, though they don't exhibit the spreading and subduction that characterize Earth's plate tectonics. Impact craters mapped by Magellan total about 1,000, distributed randomly across the surface without clustering or obvious age patterns. The craters appear remarkably pristine, showing little degradation from volcanic burial or erosion, consistent with the surface's young age. The smallest craters measure only a few kilometers across, the minimum size for impactors capable of penetrating Venus's thick atmosphere without breaking apart. Larger craters show features similar to complex craters on Earth and the Moon, including central peaks, terraced walls, and ejecta blankets. The crater distribution provides crucial constraints on surface age. If Venus had continuous volcanic activity like Earth, we would see some regions with many craters and others with few, reflecting different surface ages. Instead, the random distribution implies that the entire surface formed within a relatively brief period and has since accumulated craters steadily. Statistical analysis of crater densities gives surface ages between 300 and 600 million years, though uncertainties in cratering rates at Venus introduce significant error bars. Highland regions mapped by Magellan show complex tectonic deformation. Areas called tesserae, characterized by intersecting ridge and valley patterns, suggest compression and extension occurring in multiple phases. The formation mechanisms remain debated, with proposals ranging from mantle plumes disrupting the crust to early plate tectonic processes before the current stagnant lid regime. Some tesserae might preserve ancient crustal materials predating the global resurfacing event, offering windows into Venus's earlier geological history. Magellan's radar data also mapped Venus's topography with vertical precision approaching 100 meters. The resulting elevation models revealed that Venus has less topographic relief than Earth. About 90% of the surface lies within 1 kilometer of the mean planetary radius, compared to Earth's much greater variation from ocean trenches to mountain peaks. The planet's major highland regions, Ishtar Terra and Aphrodite Terra, rise several kilometers above the mean but occupy only a small fraction of the surface. This limited topographic variation reflects the absence of plate tectonics, which on Earth creates both deep ocean basins where plates subduct and high mountain ranges where continents collide. The Akatsuki mission revelations. Japan's Akatsuki spacecraft, orbiting Venus since 2015, has revolutionized our understanding of Venus's atmospheric dynamics through continuous monitoring at multiple wavelengths. Unlike previous missions that provided snapshots of atmospheric conditions, Akatsuki's suite of cameras images the planet continuously, revealing dynamic processes, wave phenomena, and atmospheric circulation patterns that change on timescales of hours to days. The mission has uncovered unexpected features that challenge atmospheric models and raise new questions about how Venus's thick atmosphere behaves. Akatsuki carries 5 cameras sensitive to different wavelengths from ultraviolet to mid-infrared, each probing different altitudes and atmospheric properties. The ultraviolet imager tracks the unknown UV absorbers in the clouds, revealing their distribution and motion. Infrared cameras peer through the clouds to map temperature variations, detect thermal emission from the surface at specific wavelengths, and observe cloud structure at multiple altitudes. This multi-wavelength approach provides a 3-dimensional view of atmospheric structure and dynamics. One of Akatsuki's most significant discoveries involves atmospheric gravity waves, ripples in the atmosphere created when air flows over surface topography. Despite Venus's extremely slow rotation, making wind speeds relative to the surface very low, Akatsuki detected enormous gravity waves extending thousands of kilometers across the planet, originating from airflow over highland regions. The largest stationary gravity wave, discovered in infrared images, forms a bow-shaped pattern above Aphrodite Terra, Venus's most prominent equatorial highland region. This wave remains stationary relative to the surface, even as the super-rotating atmosphere rushes overhead at hundreds of kilometers per hour. The gravity wave's formation requires specific conditions. The wind speed relative to the surface must be sufficient to disturb the atmosphere flowing over the elevated terrain, yet slow enough that the wave pattern can maintain coherence. The discovery confirms that despite the surface's slow rotation, atmospheric circulation patterns interact with topography in ways similar to mountain wave formation on Earth. These waves carry energy and momentum upward through the atmosphere, potentially contributing to the maintenance of superrotation by transferring angular momentum between different altitudes. Akatsuki has also tracked variations in Venus's superrotation over time. Wind speeds at the cloud tops vary by 10 to 20% over periods of days to weeks, with no clear pattern or periodicity. These variations coincide with changes in atmospheric temperature structure and the distribution of the unknown UV absorbers, suggesting coupling between different atmospheric properties. The causes remain unclear. Possibilities include thermal tides from solar heating, atmospheric waves propagating upward from the lower atmosphere, or internal instabilities in the circulation itself. The spacecraft observed Venus's polar vortices in unprecedented detail, revealing complex structures with multiple nested circulation cells, temperature variations, and dynamical features that change on short timescales. The vortices show elongated, irregular shapes rather than the circular patterns expected for simple polar circulation. Sometimes the vortex structure becomes unstable and breaks apart temporarily before reforming, driven by atmospheric dynamics that models struggle to reproduce. Temperature measurements from Akatsuki's infrared cameras revealed unexpected patterns in Venus's mesosphere, the atmospheric layer above the clouds extending from about 60 to 90 kilometers altitude. Instead of decreasing smoothly with altitude as expected, temperatures sometimes increase in localized regions, creating warm pockets embedded in the cooler surrounding air. And if you can do, these temperature inversions might result from atmospheric waves breaking and depositing energy or from chemical reactions that release heat. Akatsuki detected variations in Venus's albedo, the fraction of sunlight reflected back to space that correlate with atmospheric conditions. During periods when the unknown UV absorbers concentrate near the equator, the planet appears darker in ultraviolet light, absorbing more solar energy. When the absorbers disperse toward higher latitudes, the planet brightens. These albedo changes affect the amount of solar energy entering Venus's climate system, potentially driving feedback loops that influence atmospheric circulation and cloud properties. The mission also observed lightning-like electrical discharges in Venus's atmosphere, detected through radio emissions. The frequency and distribution of these events remains poorly characterized, but their occurrence confirms that Venus's clouds generate electrical charge separation similar to thunderstorms on Earth. The electrical activity might play a role in atmospheric chemistry by creating energetic particles and driving chemical reactions not possible through thermal processes alone. Future Venus missions. The renewed scientific interest in Venus has spawned numerous mission proposals aimed at answering fundamental questions about the planet's past, present, and future. Space agencies worldwide have selected or are considering missions ranging from orbital reconnaissance to long-duration surface landers and atmospheric probes. These upcoming missions promise to revolutionize our understanding of Earth's twin and test technologies needed for exploring extreme environments throughout the solar system. NASA has selected 2 Venus missions as part of its Discovery program, scheduled to launch in the late 2020s. Veritas Venus Emissivity, radio science, INSAR, topography, and spectroscopy will orbit Venus with advanced radar and infrared instruments to map surface composition, topography, and evidence for active volcanism. The mission's synthetic aperture radar will provide higher resolution than Magellan's images, revealing details down to 10 meters in scale. Veritas will also measure surface temperature variations that might indicate recent volcanic activity and map Venus's gravitational field to constrain interior structure. Da Vinci, deep atmosphere, Venus investigation of noble gases, chemistry, and imaging will drop a probe through Venus's atmosphere, sampling gases at multiple altitudes and imaging the surface during descent. The probe will measure noble gas isotopes, particularly xenon, argon, and neon, which preserve information about the planet's early history and volatile inventory. These measurements will help determine how much water Venus originally possessed and whether the planet underwent processes similar to Earth's geological evolution. Da Vinci will also analyze atmospheric chemistry, searching for trace gases that might indicate active volcanism or other processes releasing materials from the interior. The European Space Agency has selected Envision, an orbital mission that will complement NASA's efforts with radar mapping, subsurface sounding, and spectroscopic analysis. Envision's radar will search for active volcanic features by detecting surface changes between observation campaigns and measuring subtle deformations caused by magma movement beneath the surface. The subsurface sounding radar will probe below the surface, potentially detecting layered structures that preserve records of Venus's geological history. Russia's Venera D mission, under development with potential international collaboration, aims to place a long-duration lander on Venus's surface, capable of surviving for several hours despite the extreme conditions. The lander would carry advanced instruments for chemical analysis, imaging, and atmospheric measurements. Recent technological developments in high-temperature electronics and cooling systems might enable extended surface operations, dramatically increasing the scientific return compared to previous Soviet landers that survived only about 2 hours. India's space agency ISRO is developing Shukrayan-1, an orbital mission with instruments for atmospheric science, surface composition mapping, and studies of the solar-wind interaction with Venus's upper atmosphere. The mission would mark India's first dedicated Venus orbiter and contribute to the growing international fleet studying the planet. Private aerospace companies have also expressed interest in Venus exploration. Rocket Lab announced plans for a private Venus atmospheric probe mission that would deploy a small probe to sample the clouds during a brief descent before entering the hellish lower atmosphere. Such missions, enabled by decreasing launch costs and miniaturized instruments, could provide rapid, focused investigations, complementing larger governmental missions. The most ambitious proposals involve aerial platforms, balloons or aircraft that would float in Venus's temperate cloud layers for weeks or months. These platforms could carry sophisticated instruments for cloud chemistry analysis, biosignature detection, and atmospheric dynamics studies while avoiding the extreme conditions at the surface. NASA has studied concepts for Venus aerial platforms extensively, including balloon missions that would circumnavigate the planet multiple times, carried by the super-rotating winds. Sample return missions represent the ultimate goal, but face enormous technical challenges. A Venus surface sample return would require landing a spacecraft, collecting samples, launching back to orbit from the surface despite the crushing atmospheric pressure and heat, and returning to Earth all without any of the infrastructure or technologies developed for Mars missions. However, atmospheric sample return missions present fewer challenges. A probe could collect atmospheric gases during a descent through the clouds, then return to orbit for rendezvous with an Earth return vehicle. Venus and Earth's climate future. Venus serves as a natural laboratory for studying climate catastrophe, a planet-scale experiment showing what happens when greenhouse gas accumulation passes the point of no return. The lessons from Venus extend directly to Earth's climate future, providing evidence for feedback mechanisms, tipping points, and long-term consequences of atmospheric change. Understanding Venus isn't just about planetary science. It's about understanding the boundaries within which Earth-like planets remain habitable and recognizing warning signs before crossing into irreversible states. The runaway greenhouse effect that transformed Venus from a potentially habitable world to an inferno demonstrates how positive feedback loops can amplify initial warming beyond all control. The process begins with increased atmospheric greenhouse gases, carbon dioxide on Venus, carbon dioxide and other gases on Earth. These gases trap infrared radiation, warming the surface and lower atmosphere. Higher temperatures increase water vapor evaporation, and since water vapor itself is a potent greenhouse gas, this creates additional warming. On Venus, this feedback continued until oceans completely evaporated, dumping enormous amounts of water vapor into the atmosphere and driving temperatures to the point where no liquid water could exist anywhere on the planet. Earth experiences similar feedback mechanisms, but operates within different boundary conditions. Our distance from the Sun means solar input is lower, giving Earth more margin before reaching Venus-like conditions. Earth's active plate tectonics provide a long-term carbon cycle that removes carbon dioxide from the atmosphere by locking it into carbonate rocks, a regulatory mechanism Venus apparently lacks. Nevertheless, the physics governing greenhouse effects operates identically on both planets. If Earth's carbon dioxide levels rise sufficiently, particularly combined with water vapor feedback, temperatures could increase enough to trigger accelerating feedbacks that resist reversal. Climate models for Earth incorporate lessons from Venus's evolution. They include thresholds beyond which certain feedback mechanisms activate, potentially leading to state changes from which recovery becomes difficult or impossible on human timescales. For example, melting permafrost releases methane and carbon dioxide currently frozen in Arctic soils. This greenhouse gas release warms the planet further, melting more permafrost, a positive feedback. Models track numerous such feedbacks simultaneously, seeking to identify tipping points where small additional forcing triggers large, rapid changes. Venus demonstrates that planetary atmospheres have stable states separated by thresholds. Earth currently occupies a habitable stable state with moderate greenhouse effect, active carbon cycling, and abundant liquid water. Venus occupies an uninhabitable stable state with extreme greenhouse effect, no carbon removal, and no water. The transition between states, once initiated, proceeds irreversibly on geological timescales because the mechanisms that might reverse it, carbon sequestration, ocean formation, atmospheric loss, operate too slowly or cannot function under the new conditions. The deuterium to hydrogen ratio measurements from Venus provide quantitative constraints on water loss processes. Earth's hydrogen escape rate remains very low under current conditions. Our magnetic field deflects solar wind particles that might otherwise strip atmospheric gases, and our lower thermospheric temperatures limit thermal escape. However, if Earth's atmosphere warmed substantially, increasing the amount of water vapor reaching high altitudes where ultraviolet radiation breaks molecules apart, hydrogen escape rates would increase. Over geological time, this could reduce Earth's water inventory, though reaching Venus-like depletion would require sustained extreme conditions lasting billions of years. Venus's lack of magnetic field demonstrates that planets can lose this protection through changes in rotation rate or core dynamics. Earth's magnetic field has reversed polarity hundreds of times throughout geological history and will do so again in the future. During polarity transitions, the field strength decreases temporarily, potentially allowing increased atmospheric loss. However, these transitions typically occur over thousands of years, brief on geological timescales but long. Compared to human civilization, and past transitions haven't caused mass extinctions or dramatic atmospheric changes, suggesting Earth's atmosphere is resilient to temporary magnetic field variations. The study of Venus informs exoplanet research directly. Thousands of exoplanets discovered around other stars include many rocky worlds similar in size to Earth and Venus. Determining which of these planets might be habitable requires understanding the conditions that separate Earth-like from Venus-like states. The habitable zone concept, the range of orbital distances where planets can maintain liquid surface water, depends critically on atmospheric composition, greenhouse gas levels, and planetary properties like rotation rate and geological activity. Venus sits near the inner edge of our solar system's habitable zone, demonstrating that even within this zone, planets can undergo runaway greenhouse effects and lose habitability. Observations of exoplanet atmospheres using techniques like transit spectroscopy might detect biosignature gases indicating life. However, Venus teaches caution. Some gases considered potential biosignatures might also form through abiotic processes under extreme conditions. Phosphine, if confirmed in Venus's atmosphere, would illustrate that unusual chemistry can occur without biology. Distinguishing true biosignatures from exotic abiotic chemistry requires detailed understanding of planetary environments, atmospheric processes, and geochemistry knowledge built through studying planets like Venus, where we can investigate in detail. Why Venus matters more than ever. Venus has lived in Mars's shadow for too long. While rovers crawl across the red planet and plans accelerate for human missions, the nearest planet sits neglected despite holding answers to questions more urgent than Mars's ancient riverbeds or buried ice. Venus tells us how planets die. It preserves evidence of the transition from habitable world to toxic hellscape, a transformation that occurred through processes operating on Earth today. If we want to understand climate tipping points, atmospheric runaway, and the boundaries of planetary habitability, Venus provides the only accessible example of these phenomena carried to their ultimate conclusion. The scientific case for Venus exploration rests on multiple pillars. First, understanding Earth's climate system requires studying the full range of planetary climates, particularly failed states like Venus, where greenhouse effects reached extremes impossible to reproduce in laboratory experiments or computer models without real-world validation. Venus provides boundary conditions for climate science, the runaway greenhouse effect, complete ocean loss, atmospheric superrotation that test our theories under conditions far outside Earth's experience. Second, Venus preserves clues about terrestrial planet evolution that Earth has erased. Earth's active plate tectonics continuously recycles crust, destroying geological evidence older than about 4 billion years. Venus's stagnant lid tectonics might preserve ancient crustal materials dating back billions of years, offering insights into planetary formation, early atmospheres, and the conditions under which life arose on Earth. Third, the possibility, however remote, that life exists, or once existed in Venus's clouds or ancient oceans, demands investigation. If life emerged independently on Venus and Earth in the same solar system, it would revolutionize our understanding of biology's prevalence in the universe and provide a second example of biochemistry to compare with Earth's. Even if Venus is sterile, understanding why it became uninhabitable while Earth thrived matters for assessing the likelihood of life around other stars. Fourth, Venus offers a natural laboratory for extreme atmospheric physics, chemistry, and geology. The super-rotating atmosphere, sulfuric acid clouds, surface atmosphere chemical interactions, and volcanic processes all operate under conditions unattainable on Earth, providing opportunities to test fundamental theories in regimes where small effects become dominant and novel phenomena emerge. The technical challenges of Venus exploration drive innovation in materials, science, electronics, cooling systems, and spacecraft design. Developing technologies to survive Venus's surface conditions 900 degree temperatures, 90 bar pressures, corrosive atmosphere pushes engineering capabilities beyond current limits. These advances benefit not only planetary science but also terrestrial applications in extreme environments, industrial processes, and energy systems. Looking forward, the convergence of renewed scientific interest, technological capability, and international cooperation creates unprecedented opportunities for Venus exploration. Multiple missions launching in the next decade will provide the most comprehensive study of Venus since the Soviet Venera program ended 40 years ago. These missions will address fundamental questions. Is Venus volcanically active now? What processes maintain the unknown UV absorbers in the clouds? How much water did Venus originally have? Do any biosignature gases exist in the atmosphere? While raising new questions that will drive exploration for decades to come. Venus's importance extends beyond planetary science to philosophy and perspective. It demonstrates that Earth-like planets can follow divergent paths, that habitability is fragile, and that initial conditions and chance events matter profoundly for planetary outcomes. Venus and Earth formed from the same material in the same region of the solar system, yet evolved into heaven and hell. This cosmic accident of fate, Venus slightly closer to the Sun, perhaps struck by different impactors, maybe lacking the moon that stabilized Earth's rotation, resulted in one planet nurturing life for billions of years, while its twin became the solar system's most hostile environment. The lesson is humility. We occupy a planet balanced precariously between stability and catastrophe, kept habitable by mechanisms we still don't fully understand, threatened by changes we're only beginning to measure. Venus shows us what losing that balance looks like, preserved in scorched rock and poisonous clouds, a warning written in planetary physics for anyone willing to read it. Ignoring Venus is ignoring the possibility that Earth's climate could cross similar thresholds, that atmospheric change can become irreversible, that we might be pushing systems toward tipping points we won't recognize until we've passed them. The most important planet we've ignored holds the knowledge we most need: how to recognize the difference between a world that lives and a world that dies, and what we must do to ensure Earth never follows Venus into oblivion. That makes Venus not just interesting, not just scientifically valuable, but essential to understanding our own planet's future and our responsibility as its temporary stewards. The thermal inertia paradox. Venus's surface temperature remains constant at 900 degrees Fahrenheit, regardless of day or night, equator or pole, facing the sun or in shadow. This uniform heat distribution defies simple expectations and reveals fundamental principles about how thick atmospheres transport and redistribute energy. On Earth, temperatures vary dramatically between day and night, summer and winter, tropics and poles, because our relatively thin atmosphere cannot efficiently move heat fast enough to eliminate these differences. Venus's atmosphere, 92 times more massive and far thicker, operates under entirely different physics that erases all temperature variation through mechanisms that took decades to understand fully. The uniformity results from atmospheric circulation powered by the extreme greenhouse effect itself. Heat absorbed at the surface radiates as infrared radiation, immediately trapped by carbon dioxide molecules in the overlying atmosphere. This energy cannot escape directly to space instead. It gets absorbed and re-emitted countless times as it slowly diffuses upward through the dense atmospheric column. The process takes so long that atmospheric motions transport heat laterally much faster than it can escape vertically. Winds in the middle atmosphere, moving at tens of meters per second, carry heat from the day side to the night side continuously, distributing thermal energy around the planet before it can radiate away. Computer models simulating Venus's atmospheric circulation reproduce this temperature uniformity only when they include detailed radiative transfer physics. The carbon dioxide atmosphere absorbs and emits infrared radiation at specific wavelengths corresponding to molecular vibration frequencies. Photons emitted by the hot surface get absorbed within meters of their origin, heating the surrounding gas. That gas re-emits infrared in all directions, some downward, reheating the surface, some upward, where it gets absorbed again a short distance away. This repeated absorption and emission, called radiative diffusion, locks heat within the lower atmosphere while circulation distributes it horizontally. The thick atmosphere also has enormous heat capacity, the amount of energy required to change its temperature. The total thermal mass of Venus's atmosphere exceeds Earth's atmosphere by orders of magnitude. This massive reservoir of heat stored in atmospheric gases acts as a thermal buffer, smoothing out any temperature variations that might arise from uneven heating. Even if one region receives more solar energy temporarily, the excess heat quickly disperses into the surrounding massive atmosphere, raising the temperature imperceptibly. The dense lower atmosphere near the surface moves sluggishly despite the vigorous circulation aloft. Surface wind speeds typically measure only a few kilometers per hour because the high density means even slow motions carry enormous momentum and energy. These gentle but powerful flows, combined with radiative diffusion, homogenize surface temperatures across all longitudes and latitudes. Measurements from Soviet Venera landers confirm this uniformity. Landing sites separated by thousands of kilometers at different latitudes and times of day, all recorded temperatures within a few degrees of 735 Kelvin. The day-night temperature equality particularly demonstrates the efficiency of atmospheric heat transport. Venus's slow rotation means the day side faces the sun for nearly 2 Earth months continuously, while the night side languishes in darkness for an equally long period. Without atmospheric circulation, the day side should heat to temperatures far exceeding observed values, while the night side should cool substantially. Instead, the super-rotating winds carry heat from day to night fast enough to maintain equilibrium. The atmosphere circles the planet every 4 Earth days, meaning air parcels experience dozens of day-night cycles during one Venusian solar day, thoroughly mixing and homogenizing their thermal energy. This thermal inertia affects Venus's infrared emission to space. Observations from Earth and spacecraft show Venus radiates energy almost uniformly across its entire disk, not just from the sunlit hemisphere. The planet's energy budget balances on global scales. Total absorbed solar energy equals total emitted infrared radiation when averaged over the entire surface in sufficient time. The redistribution mechanisms ensure this balance occurs uniformly rather than with hot spots and cold zones. Understanding Venus's thermal inertia informs climate science beyond planetary applications. It demonstrates how atmospheric mass, composition, and circulation couple to determine surface temperature patterns. Thick atmospheres on exoplanets, particularly those orbiting close to their stars where tidal locking might create permanent day and night sides, could exhibit similar heat redistribution. Models of such planets incorporate lessons from Venus that superrotation and efficient heat transport can maintain habitable conditions on the night side of tidally locked worlds, despite receiving no direct sunlight, dramatically expanding the potential habitable zone around certain stars. The uniformity also affects geological processes. On Earth, temperature variations drive weathering patterns, with different minerals stable at different latitudes and elevations. Venus's isothermal surface experiences identical chemical weathering conditions everywhere, potentially producing more uniform surface compositions than Earth's diverse climatic zones create. However, pressure variations with elevation small compared to Earth's atmospheric pressure changes, but significant relative to Venus's uniformity, do create different chemical equilibria at different altitudes, allowing some mineralogical variation in highland versus lowland regions. Recent infrared observations from spacecraft have detected subtle temperature variations at Venus's surface, typically just a few degrees associated with topographic features. Highland regions show slightly cooler temperatures than lowlands due to lower atmospheric pressure, reducing the greenhouse effect strength slightly. These tiny variations, measurable only with sensitive instruments, confirm theoretical predictions and provide additional constraints on atmospheric circulation models. The variations also create weak thermal winds, air movements driven by temperature gradients that might influence the formation of gravity waves observed over highland regions. The isotope signatures of lost water. The story of Venus's vanished oceans is written in the isotopic composition of hydrogen remaining in its atmosphere. Isotopes, atoms of the same element with different numbers of neutrons, behave almost identically in chemical reactions, but differ subtly in physical properties like mass and diffusion rates. These differences create isotopic fractionation when processes preferentially remove or retain certain isotopes, leaving signatures that reveal the planet's history billions of years after the events occurred. Hydrogen exists primarily as regular hydrogen with one proton and one neutron, but about 0.015% of Earth's hydrogen consists of deuterium, containing one proton and one neutron. Venus's atmospheric hydrogen shows deuterium enrichment factors of 120 to 150 times Earth's ratio, a staggering difference that requires explanation through massive preferential loss of regular hydrogen over geological time. The mechanism involves photodissociation of water molecules in Venus's upper atmosphere. Solar ultraviolet radiation, particularly wavelengths shorter than 200 nanometers, carries enough energy to break the chemical bonds holding water molecules together, splitting H2O into hydrogen and oxygen, or into hydroxyl radicals that subsequently break down. This process occurs in the thermosphere and exosphere, the uppermost atmospheric layers where gas densities become extremely low and temperatures reach thousands of degrees. Once freed from molecules, individual hydrogen atoms can escape to space if they possess sufficient velocity to overcome Venus's gravity. Regular hydrogen, with atomic mass of approximately 1 atomic mass unit, escapes more readily than deuterium, with atomic mass of approximately 2. At the high temperatures in Venus's exosphere, the thermal velocity distribution of atoms follows Maxwell-Boltzmann statistics, with lighter atoms achieving higher average speeds. Hydrogen atoms exceed Venus's escape velocity far more frequently than deuterium atoms, creating preferential loss that gradually enriches the remaining atmospheric inventory in the heavier isotope. Over billions of years, this fractionation process amplified the deuterium to hydrogen ratio from primordial values similar to Earth's to the extreme enrichment observed today. Quantifying the total water loss from isotopic measurements requires modeling the escape process over Venus's entire history. The calculations depend on assumptions about initial water inventory, escape rates as functions of solar radiation intensity, atmospheric composition changes over time, and the efficiency of isotopic fractionation. Different research groups have produced estimates ranging from water equivalent to Earth's oceans to as little as 10% of that amount, reflecting uncertainties in the model parameters. The consensus suggests Venus originally possessed substantial water enough to form oceans covering the surface to depths of at least tens of meters, possibly hundreds of meters or more. Measurements of other isotopes provide additional constraints. Oxygen. Isotopes: oxygen 1,6, oxygen 1,7, and oxygen 1,8 show enrichment patterns in Venus's atmosphere consistent with preferential loss of lighter isotopes. When water molecules break apart, the freed oxygen atoms can react with carbon dioxide, sulfur dioxide, or other atmospheric constituents. Some oxygen escapes to space, while some reacts with surface minerals, gradually altering the isotopic composition of both atmosphere and surface. The observed oxygen isotope ratios, measured by spacecraft mass spectrometers, indicate substantial oxygen loss accompanying hydrogen escape, though the exact amounts remain uncertain due to oxygen's participation in multiple atmospheric and surface chemical reactions. Neon isotopes offer another window into Venus's volatile history. Neon, being a noble gas, doesn't participate in chemical reactions, but can escape to space through physical processes. The ratio of neon, 20 to neon 22 inches, Venus's atmosphere differs slightly from solar values, suggesting some neon loss occurred. However, neon's greater mass compared to hydrogen means escape proceeds far more slowly, preserving a record closer to Venus's original volatile composition. Measuring neon and other noble gas isotopes with high precision requires direct atmospheric sampling, a key objective of the proposed Da Vinci mission. Comparing isotope ratios across multiple elements, hydrogen, oxygen, neon, argon, xenon, will constrain models of atmospheric evolution, potentially discriminating between scenarios involving different water inventories, escape mechanisms, and timescales. These measurements essentially reconstruct Venus's climate history through chemistry, reading the signatures of ancient oceans in the atomic nuclei of molecules floating in the present-day atmosphere. The extreme deuterium enrichment also affects atmospheric chemistry subtly. Deuterium substitution in molecules slightly alters reaction rates and equilibrium constants due to quantum mechanical isotope effects that become measurable at Venus's enrichment levels. Molecules containing deuterium break apart more slowly under ultraviolet radiation than their regular hydrogen counterparts, because the heavier deuterium creates stronger effective bonds. This influences the photochemical balance in Venus's upper atmosphere, affecting the distribution of molecules like hydrogen deuteride versus molecular hydrogen, water with deuterium versus regular water, and other deuterated species. Recent ground-based spectroscopic observations have detected multiple deuterated molecules in Venus's atmosphere: HDO, water with 1 deuterium, DCl deuterium chloride, and others at abundances reflecting the overall deuterium enrichment. Mapping the spatial and temporal variations of these species provides information about atmospheric mixing, photochemistry, and the coupling between different atmospheric layers. The role of solar wind stripping. Venus's lack of a protective magnetic field exposes its upper atmosphere directly to the solar wind, a continuous stream of charged particles flowing outward from the Sun at speeds of 400 to 800 kilometers per second. This interaction drives atmospheric erosion processes that have stripped away significant amounts of gas over billions of years, contributing to the planet's evolution from potentially habitable to its current state. Understanding solar wind stripping requires examining the complex physics of how charged particles interact with planetary atmospheres and the long-term consequences for atmospheric retention. The solar wind consists primarily of protons and electrons, with smaller amounts of helium nuclei and trace heavier ions, all carrying the Sun's magnetic field embedded within the flow. When this magnetized plasma encounters a planet with a strong intrinsic magnetic field like Earth, the field deflects the solar wind around the planet, creating a protective magnetosphere. Venus's weak or absent intrinsic field provides no such protection. Instead, the solar wind impacts the upper atmosphere directly, interacting with ionized atmospheric gases to create an induced magnetosphere. The interaction begins at the ionosphere, the atmospheric layer where solar ultraviolet radiation has stripped electrons from neutral atoms and molecules, creating a population of charged ions and free electrons. The solar wind's embedded magnetic field cannot penetrate this conducting plasma easily, so magnetic pressure builds up and diverts the flow around the obstacle, creating a bow shock where the supersonic solar wind slows abruptly. The boundary between the shocked solar wind and the ionosphere, called the ionopause, marks the effective obstacle the solar wind encounters. Below this boundary, Venus's atmosphere remains relatively protected. Above it, atmospheric ions can interact directly with solar wind particles and escape. Several mechanisms contribute to atmospheric escape. Pickup ion loss occurs when neutral atoms from Venus's extended exosphere, the outermost atmospheric layer, where densities are so low that atoms rarely collide, become ionized by solar ultraviolet radiation or charge exchange with solar wind protons. These newly ionized atoms immediately feel the electromagnetic forces from the solar wind's magnetic field and get accelerated to high velocities, often exceeding escape velocity. The solar wind essentially picks up these ions and carries them away from the planet. Sputtering represents another loss mechanism. Energetic particles from the solar wind penetrate into the upper atmosphere and collide with atmospheric atoms and molecules. These collisions transfer momentum, occasionally giving atmospheric particles enough energy to escape even if they're too heavy to escape through thermal processes alone. Sputtering can remove heavier species like oxygen and carbon that don't readily escape through other mechanisms. The Venus Express mission carried instruments specifically designed to measure atmospheric escape processes. Its analyzer of space plasmas and energetic atoms mapped the distribution of escaping ions around Venus, detecting beams of oxygen, hydrogen, helium, and even heavier ions flowing away from the planet. The measurements revealed asymmetries in the escape pattern. More ions escape from the side of Venus facing away from the Sun, the night side, than from the day side. This counterintuitive result occurs because magnetic field lines draping around Venus from the solar wind provide pathways for ions to escape more efficiently from certain regions. Quantifying total atmospheric loss through solar wind interactions requires integrating escape rates over billions of years and accounting for how these rates changed as the Sun evolved. The young Sun, during its first billion years, emitted far more intense ultraviolet radiation and produced a denser, faster solar wind than today. This enhanced early solar activity would have driven much higher atmospheric escape rates, potentially removing the equivalent of Earth's atmosphere from Venus within the first billion years if no replenishment occurred. However, volcanic outgassing continuously replaced lost gases, creating a competition between loss and supply that determined the net atmospheric evolution. Models of Venus's atmospheric evolution, incorporating solar wind stripping, along with thermal escape, impact erosion, and volcanic replenishment, suggest that water loss occurred primarily through photodissociation and hydrogen escape, rather than direct removal of water molecules by the solar wind. The deuterium enrichment supports this interpretation. Solar wind pickup doesn't fractionate isotopes as strongly as thermal escape does, so the extreme deuterium enrichment indicates thermal processes dominated. Nevertheless, solar-wind interactions contributed significantly to oxygen loss and may have removed other volatile species over geological time. The lack of a magnetic field affects not only atmospheric loss but also surface exposure to radiation. Earth's magnetosphere shields the surface from most solar wind particles and cosmic rays, with only occasional exposure during magnetic storms. Venus's surface and lower atmosphere experience continuous bombardment by energetic particles that penetrate deep into the atmosphere. This radiation environment affects atmospheric chemistry, potentially driving reactions that wouldn't occur through thermal processes alone, and complicates the potential for life in Venus's clouds by adding radiation damage to the list of challenges hypothetical organisms would face. Recent observations from NASA's Parker Solar Probe, which flies past Venus during gravitational assist maneuvers on its journey toward the Sun, have provided new data on the solar-wind interaction. During a close flyby in 2021, Parker Solar Probe detected radio emissions from Venus's ionosphere, natural radio waves generated by instabilities in the plasma as the solar wind flows around the planet. These observations complement Venus Express measurements and help refine models of the induced magnetosphere structure and dynamics. The pressure cooker surface chemistry. Venus's surface exists under conditions so extreme that chemical reactions impossible on Earth occur continuously, driven by the combination of high temperature, crushing pressure, and reactive atmospheric composition. The surface environment creates a natural laboratory for studying chemistry at extremes, with implications for understanding geological processes, industrial applications, and exotic environments throughout the universe. The interplay between surface mineralogy and atmospheric gases drives weathering reactions that alter rocks and possibly help regulate atmospheric composition over geological timescales. At 735 Kelvin and 92 bars pressure, many chemical reactions reach equilibrium states dramatically different from those at Earth's surface. Minerals stable in Earth's crust decompose or transform at Venus's conditions, while substances unstable on Earth become preferred products. The high temperature provides abundant thermal energy to overcome activation barriers, allowing reactions to proceed rapidly that would take geological ages under cooler conditions. The high pressure favors reactions that reduce volume, combining multiple molecules into fewer, denser products. Carbon dioxide, dominating the atmosphere at 96% abundance, reacts with calcium-bearing minerals at the surface to form carbonates. On Earth, this reaction occurs primarily in the oceans, where dissolved CO2 reacts with calcium ions to precipitate calcium carbonate limestone. Venus lacks liquid water, but the high temperature and pressure allow gas-solid reactions between atmospheric CO2 and surface rocks containing calcium silicates. The reaction forms calcium carbonate plus silica, locking atmospheric carbon into surface minerals. However, at Venus's surface temperature, calcium carbonate remains stable only at certain pressure ranges. Some models suggest carbonates in lowland regions might decompose, releasing CO2 back to the atmosphere, while highland regions maintain carbonate stability. This creates a potential feedback mechanism where topography influences atmospheric composition through pressure-dependent weathering equilibria. Sulfur chemistry at Venus's surface involves complex interactions between atmospheric sulfur dioxide, surface minerals, and trace atmospheric constituents. Sulfur dioxide can react with iron-bearing minerals to form iron sulfides, pyrite, and related compounds, through reactions energetically favorable at high temperatures. These sulfides alter radar reflectivity and color, potentially explaining some observed surface features. The reactions also lock atmospheric sulfur into the surface, providing a sink that must be balanced by volcanic replenishment to maintain observed sulfur dioxide levels. Some researchers propose that variations in sulfur dioxide abundance observed by different missions over decades reflect changes in volcanic activity, with eruptions injecting fresh SO2 that gradually gets removed through surface reactions and atmospheric photochemistry. Water, though present only as trace vapor in the atmosphere, participates in surface chemistry through its effect on mineral stability and reaction rates. Hydrated minerals containing water molecules within their crystal structure decompose at Venus's surface, releasing water vapor to the atmosphere. Conversely, some anhydrous minerals might incorporate trace atmospheric water under certain conditions. The balance between dehydration and hydration reactions depends on the atmospheric water vapor, partial pressure and temperature, creating altitude-dependent zones where different minerals remain stable. Radar observations showing unusual reflectivity in highland regions have been interpreted as indicating ferroelectric minerals such as pyrite or other sulfides, whose properties change at specific temperature thresholds. The highlands, being cooler than lowlands due to elevation, cross into temperature ranges where certain minerals undergo phase transitions or chemical changes that dramatically alter their interaction with radar waves. Testing these hypotheses requires sampling highland materials, a major challenge given the difficulty of operating spacecraft at Venus's surface, and the even greater challenge of accessing high elevation regions. The atmosphere's chemical composition at the surface differs from higher altitudes due to thermodynamic equilibria shifting with pressure and temperature. Some gases that exist in trace amounts in the upper atmosphere become more or less abundant near the surface as reactions reach different equilibrium states. For example, carbonyl sulfide (OCS) forms from reactions between carbon dioxide and sulfur-bearing gases and reaches different concentrations depending on altitude. Mapping these vertical chemical gradients provides information about atmospheric mixing rates and reaction kinetics. Experimental studies attempting to recreate Venus surface conditions in laboratories face significant challenges. Achieving both 735 Kelvin and 92 bars simultaneously in a controlled environment that allows chemical analysis requires specialized equipment. Several laboratories have constructed Venus surface simulation chambers, pressure vessels heated to Venusian temperatures and filled with carbon dioxide at appropriate pressures to study mineral stability and reaction. Kinetics. These experiments have demonstrated that many reactions predicted from thermodynamic calculations do occur under Venus conditions, validating theoretical models and identifying unexpected reaction products that inform interpretation of spacecraft measurements. The global resurfacing debate, the question of whether Venus underwent a single catastrophic global resurfacing event or experiences ongoing spatially distributed volcanism, remains one of the most contentious debates in planetary geology. The answer has profound implications for understanding Venus's interior dynamics, volcanic processes, and how planets without plate tectonics release internal heat. Evidence supporting both scenarios exists, and resolving the debate requires additional observations of surface change, volcanic activity, and theoretical modelling of mantle convection beneath a stagnant lithosphere. The global resurfacing hypothesis emerged from analysis of Magellan's impact crater catalogue. The approximately 1,000 craters detected show no clustering or obvious age patterns. They appear randomly distributed across the surface, as if they accumulated steadily over a uniform age terrain. Statistical analyses of crater spatial distributions, size-frequency relationships, and superposition patterns found no evidence for differently aged geological provinces. This uniformity suggests the entire surface formed within a relatively brief period, perhaps 100 million years, then accumulated craters uniformly afterward as volcanic activity decreased to levels insufficient to bury new impact craters. Theoretical support for episodic resurfacing comes from models of stagnant lid convection. Unlike Earth, where plate tectonics continuously recycles the lithosphere and releases heat, Venus's single-plate lid insulates the interior. Heat from radioactive decay and residual primordial heat accumulates beneath the stagnant lid, gradually raising temperatures in the upper mantle. Eventually, the lithosphere heats enough to weaken mechanically or partially melt at its base. This triggers widespread volcanism as magma breaks through the weakened lid in numerous locations, flooding vast areas with lava and creating the observed plains. The massive eruptions release accumulated heat, cooling the upper mantle and allowing the lithosphere to solidify into a new stagnant lid. The cycle then repeats on timescales of hundreds of millions to 1 billion years. Computer simulations implementing these physics can reproduce episodic resurfacing. Models start with a stagnant lid overlying a convecting mantle. Heat accumulates, the lithosphere weakens, and the model develops numerous volcanic centers that remain active for tens of millions of years before shutting down as the system cools. The simulated resurfacing events produce surfaces with crater statistics similar to Venus's observed distribution, supporting the catastrophic resurfacing interpretation. However, alternative interpretations challenge this scenario. Some researchers argue that small amounts of ongoing volcanism, localized in certain regions, could maintain the observed crater distribution if the resurfacing rate roughly balances the cratering rate. In this equilibrium resurfacing model, Venus experiences continuous but spatially heterogeneous volcanism that obliterates craters as they form in some regions while allowing crater accumulation elsewhere. The net result appears as random crater distribution without requiring global catastrophism. Evidence for recent or ongoing volcanism comes from multiple sources. Variations in atmospheric sulfur dioxide concentration measured by different missions spanning decades might indicate sporadic volcanic injections of fresh SO2. The Venus Express mission detected sulfur dioxide decreasing significantly during its 8-year mission, potentially reflecting the slow decay of a volcanic injection that occurred before the spacecraft arrived. More recent observations show sulfur dioxide levels increasing again, suggesting either new volcanic activity or complex atmospheric circulation patterns, bringing deeper sulfur-rich air to observable altitudes. Infrared observations searching for thermal hotspots indicative of active lava flows have produced ambiguous results. Some studies report localized temperature anomalies consistent with fresh volcanic deposits cooling over time, while others attribute the same features to variations in surface emissivity or atmospheric effects. Definitive detection of active volcanism requires observing the same region repeatedly with sufficient resolution and thermal sensitivity to detect changes, a capability no mission has yet achieved but future missions will provide. The global resurfacing debate also involves Venus's interior structure and thermal evolution. Seismic data unavailable for Venus would constrain mantle structure, convection patterns, and the presence of a partially molten layer beneath the lithosphere. On Earth, seismology revealed the structure of the mantle and core, plate boundaries, and magma chambers. Venus lacks seismic stations, leaving its interior structure poorly constrained. Models rely on gravity field measurements, topography, and theoretical calculations based on Venus's size, mass, and likely composition. Recent reanalysis of Magellan gravity data suggests some regions show gravity anomalies consistent with active mantle plumes, rising columns of hot rock from deep within the planet. These plumes might drive localized volcanism, creating coronae and volcanic clusters without requiring global resurfacing. The distribution and vigor of plumes depends on mantle convection patterns, which in turn depend on the planet's thermal state and the efficiency of heat loss through the stagnant lid. Reconciling the crater statistics with ongoing volcanism requires that volcanic resurfacing rates remain low enough not to create obvious age variations, but high enough to affect atmospheric chemistry through degassing. This balances on a narrow parameter range, making predictions testable through future observations. Missions capable of detecting surface changes by comparing radar images separated by decades could identify actively flowing lava, growing volcanic edifices, or new craters forming in regions resurfaced since Magellan. Such observations would revolutionize understanding of Venus's volcanic activity and resolve the resurfacing debate. Venus analogues on exoplanets. Thousands of exoplanets discovered around other stars include many rocky worlds similar in size to Venus and Earth, orbiting at distances where surface conditions might range from temperate to infernal. Identifying which exoplanets resemble Venus versus Earth has become a critical challenge in astrobiology and planetary science, because the difference determines habitability. Venus serves as the primary example of a rocky planet that likely started habitable but underwent climate catastrophe, providing a cautionary template for interpreting observations of distant worlds. we can study only through starlight filtering through their atmospheres. The concept of the habitable zone, the range of orbital distances where liquid water can exist on a planet's surface, emerged decades ago as a simple way to assess habitability potential. Planets orbiting too close to their stars receive too much energy and become too hot for liquid water. Those too far receive too little and freeze. Earth sits comfortably within the Sun's habitable zone. Venus, at 0.72 astronomical units, lies near the inner edge. Some models place it just inside the habitable zone, others just outside, depending on assumptions about atmospheric composition and reflectivity. This ambiguity highlights the problem with simple habitable zone definitions. They typically assume Earth-like atmospheres and don't account for runaway greenhouse effects, atmospheric loss, or the complex feedbacks that determine actual surface conditions. Venus demonstrates that planets within the traditionally defined habitable zone can be utterly uninhabitable if atmospheric evolution follows certain pathways. Exoplanet characterization relies primarily on transit spectroscopy, analyzing starlight that passes through a planet's atmosphere during transits across its star's disk. Different molecules absorb light at characteristic wavelengths, creating spectral features that reveal atmospheric composition. By identifying which gases exist and estimating their abundances, astronomers infer surface conditions, climate, and potentially biosignatures. For Venus-like exoplanets, several atmospheric signatures would indicate hostile conditions. High carbon dioxide abundance combined with high atmospheric mass suggests intense greenhouse effects. Sulfur dioxide presence at high altitudes indicates volcanic activity. Absence of water vapor or extremely low abundances implies lost oceans. Detection of high-altitude hazes or clouds might indicate sulfuric acid layers similar to Venus. Combining multiple signatures builds a picture distinguishing Venus-like from Earth-like atmospheres. Several confirmed exoplanets likely resemble Venus more than Earth: TRAPPIST, 1b and c. The two innermost planets in the famous seven-planet system orbiting an ultra-cool dwarf star receive stellar energy fluxes similar to or exceeding Venus's. Models suggest they likely possess thick CO2 atmospheres, with surface temperatures potentially reaching or exceeding Venus's depending on their actual atmospheric compositions. The James Webb Space Telescope began observing these planets in 2023, attempting to detect atmospheric signatures through transit spectroscopy. GJ 1132b, orbiting a red dwarf star about 39 light-years away, shows evidence for a thick atmosphere despite receiving intense stellar radiation that should have stripped atmospheric gases over billions of years. Observations suggest possible volcanic outgassing, continuously replenishing the atmosphere, a scenario similar to proposed mechanisms maintaining Venus's atmosphere against solar wind erosion. The planet's atmosphere might resemble Venus's, dominated by CO2 and volcanic gases, creating a hellish environment despite being slightly larger than Earth. The challenge of distinguishing Venus-like from Earth-like exoplanets drives mission concepts like the proposed large UV, optical, IR surveyor, LUVOIR, a space telescope capable of directly imaging rocky exoplanets and analysing their atmospheres with far greater detail than transit spectroscopy allows. Such missions could detect atmospheric oxygen and water vapour, indicating habitability or carbon dioxide and sulfur dioxide suggesting Venus-like conditions, finally answering which nearby exoplanets merit deeper investigation for biosignatures. Understanding Venus's evolution informs models predicting exoplanet habitability. The transition from potentially habitable early Venus to the current state occurred through mechanisms that should operate on similar planets' proximity to the host star: greenhouse gas accumulation, water loss through photodissociation and escape. By studying Venus in detail, planetary scientists constrain parameters in habitability models, improving predictions about which exoplanets likely remain habitable and which underwent Venus-like transformations. Statistical studies of exoplanet populations reveal that Venus-sized planets are extremely common, particularly around M-dwarf stars, which constitute 70% of all stars in the galaxy. Many of these planets orbit close enough to receive stellar energy comparable to Venus, placing them at risk for runaway greenhouse effects. If a significant fraction became Venus-like rather than remaining habitable, this would dramatically reduce the number of potentially habitable worlds in the galaxy, affecting estimates of life's prevalence. The possibility that some exoplanets transition between habitable and uninhabitable states over their lifetimes adds temporal complexity. A planet might remain habitable for billions of years before crossing a threshold into runaway greenhouse conditions, similar to Venus's proposed history. Detecting such planets during their habitable phases versus their post-runaway phases would yield completely different interpretations of the same world, emphasizing the need to understand planetary climate evolution over billions of years, not just present-day conditions. The quest for active volcanism. Determining whether Venus currently experiences active volcanism represents one of the most important unsolved questions in planetary science, with implications for understanding the planet's interior dynamics, atmospheric chemistry, and geological evolution. Unlike Mars, where rovers can directly sample and date rocks, or Io, where spacecraft have photographed erupting volcanoes in real time, Venus's thick clouds and hostile surface conditions make detecting ongoing volcanic activity extraordinarily difficult. Yet multiple lines of indirect evidence suggest that Venus might still be volcanically active today, potentially experiencing eruptions that reshape portions of the surface and inject fresh gases into the atmosphere on timescales of years to decades. The case for recent volcanism rests primarily on atmospheric chemistry observations. Sulfur dioxide, detected in Venus's atmosphere since the 1970s, exists predominantly in the middle and upper atmosphere, where it plays a crucial role in cloud formation and photochemistry. Sulfur dioxide gets destroyed relatively quickly through reactions with other atmospheric constituents and photochemical breakdown driven by solar ultraviolet radiation. The destruction time scales range from a few years at high altitudes to decades in the middle atmosphere. Without continuous replenishment, sulfur dioxide concentrations should decline steadily until reaching negligible levels. Yet observations show so too persists at detectable levels, with concentrations that vary significantly over time. Pioneer Venus, which orbited from 1978 to 1992, measured sulfur dioxide concentrations in the upper atmosphere and detected a dramatic decrease over its mission lifetime. SO2 levels dropped by a factor of 10 during the spacecraft's operational period. The simplest explanation invoked a major volcanic eruption occurring shortly before or during the early Pioneer Venus mission that injected a massive pulse of sulfur dioxide into the atmosphere. As years passed, photochemical destruction gradually removed the volcanic SO2, causing the observed decline. This interpretation suggests Venus experienced significant volcanic activity as recently as the late 1970s or early 1980s. However, alternative explanations challenge this conclusion. Atmospheric circulation patterns change over time, potentially bringing sulfur-rich air from the lower atmosphere to higher altitudes where measurements occur, then later shifting to circulation patterns that isolate the upper atmosphere from lower sources. Such dynamical variations could mimic the signature of volcanic injection and decay without requiring actual eruptions. Distinguishing between volcanic and dynamical causes requires understanding Venus's atmospheric circulation in far greater detail than available from single spacecraft missions with limited temporal coverage. The Venus Express mission, arriving at Venus in 2006, provided a new opportunity to search for volcanic signals. Its spectrometers measured sulfur dioxide abundances and detected significant variations over the spacecraft's 8-year mission, though the patterns differed from Pioneer Venus observations. Some regions showed increasing SO2 concentrations while others decreased, suggesting either localized volcanic sources or complex atmospheric transport that varied spatially. The mission also detected transient hotspots in thermal infrared images, localized regions showing higher temperatures than their surroundings. Some of these hotspots appeared over known volcanic features like Idun Mons and Imdar Reggio, raising the possibility that they represented cooling lava flows or recently erupted deposits still radiating excess heat. Detailed analysis of the thermal anomalies attempted to determine whether they required active volcanism or could result from variations in surface emissivity. How efficiently surfaces radiate thermal energy at different wavelengths. Different rock types and weathering states produce different emissivities, potentially creating apparent temperature variations in infrared images, even when actual temperatures remain uniform. Discriminating between true temperature variations and emissivity effects requires observations at multiple wavelengths and sophisticated radiative transfer modeling. The Venus Express team concluded that some hotspots likely represented genuine thermal anomalies consistent with recent volcanic activity. though absolute confirmation remained elusive. Ground-based observations complement spacecraft measurements. Radio telescopes monitoring Venus at millimeter wavelengths can detect sulfur dioxide through its spectral signature and track concentration changes over time. Observations spanning multiple years have confirmed that sulfur dioxide abundances vary, with timescales ranging from months to years. Some variations correlate with solar activity cycles, suggesting solar radiation affects atmospheric chemistry and circulation patterns. Other variations show no obvious correlation with external factors, potentially indicating internal geological processes like volcanism. The search for active volcanism also examines surface changes directly. Comparing radar images from different missions separated by decades could reveal new lava flows, growing volcanic domes, or other surface modifications. However, Magellan remains the only mission to map Venus's surface at high resolution, making direct comparison difficult. Some researchers have attempted to compare lower-resolution radar images from earlier missions or ground-based telescopes with Magellan data, searching for changes. A few studies reported possible surface changes, small regions showing different radar properties in images separated by years, but the low resolution and different viewing geometries make definitive conclusions impossible. Future missions promise to resolve the active volcanism question. The Veritas mission will carry synthetic aperture radar capable of detecting surface changes by comparing its images with Magellan data from 3 decades earlier. Any lava flows erupted since 1994 should appear as fresh surfaces with different textures and radar properties than their surroundings. Veritas will also measure surface temperature variations with improved sensitivity, identifying thermal hotspots that might indicate recent eruptions. The mission's interferometric synthetic aperture radar will detect subtle ground deformation, centimeter-scale changes in surface elevation caused by magma movement beneath volcanoes, similar to how radar satellites monitor active volcanoes on Earth. The EnVision mission will carry similar capabilities, with additional instruments for compositional analysis and subsurface sounding. Together, these missions will monitor Venus continuously over multiple years, providing the temporal coverage needed to detect eruptions if they occur during the mission's operational periods. Even if no eruptions occur during observation, comparing surface and atmospheric data with historical measurements will constrain volcanic activity rates, determining whether Venus experiences frequent small eruptions, rare large eruptions, or no significant volcanism in recent geological time. Understanding Venus's current volcanic activity connects to broader questions about stagnant lid tectonics and planetary heat loss. Computer models of mantle convection beneath stagnant lids predict different outcomes depending on parameters like mantle viscosity, lithosphere thickness, and internal heat production rates. Some models produce episodic catastrophic resurfacing with long quiescent periods between events. Others generate continuous low-level volcanism from mantle plumes that penetrate the lithosphere locally without triggering global resurfacing. Still, others predict that planets like Venus should have essentially no volcanism at present if the last major resurfacing occurred hundreds of millions of years ago, and the lithosphere has since cooled and thickened beyond the point where magma can easily breach the surface. Evidence for active volcanism would support models with ongoing mantle plumes and relatively thin or weak lithosphere. Absence of detectable activity would favour models with thicker lids and lower current heat flow, suggesting Venus might be in a quiescent phase between major resurfacing events. Either outcome constrains Venus's thermal evolution and interior state. Helping planetary scientists understand how terrestrial planets without plate tectonics evolve over billions of years, knowledge applicable to exoplanets, where stagnant lid tectonics might be the norm rather than the exception. The volcanic question also bears on atmospheric evolution and potential habitability. If Venus experiences ongoing volcanism, the continuous injection of water vapor, sulfur dioxide, and other gases affects atmospheric chemistry and potentially creates localized environments in volcanic plumes where conditions differ from the ambient atmosphere. Some researchers speculate that volcanic outgassing might periodically inject enough water vapor to create transient habitable niches in the clouds, though this remains highly speculative. Conversely, if volcanism has ceased, Venus's atmosphere becomes a closed system, evolving only through photochemistry and atmospheric escape, simplifying models of long-term atmospheric evolution. Definitive answers require direct observation of erupting volcanoes or fresh lava flows. The probability of catching an eruption in progress depends on eruption frequency and duration. If Venus averages one major eruption per decade lasting weeks to months, missions observing for several years have reasonable chances of detecting activity. If eruptions occur only once per century or less, detection becomes unlikely without long-duration monitoring. Continuous observation from multiple spacecraft in different orbits, combined with ground-based monitoring during favourable viewing geometries, maximizes detection probability and will finally answer whether Venus remains a volcanically living world or has entered geological quiescence.